Suppose the question says, solve this differential equation. First of all, x equal to 0 is going to be a singular point, and it's a regular singular point. X equal to 0 is a regular singular point. Why is that? Because x times 1 over 3x is going to be a third, which is analytic. Also, x squared times -1 divided by 3x, which is negative x divided by 3, is also analytic. So it means that x equal to 0 is a regular singular point. So the Frobenius theorem guarantees that we have a power series solution of the form of y equals to the sum Cn x to power n plus r and start from 0 to infinity. This y can be written as c sub 0 x to the r plus c sub 1 x to r plus 1 plus c2 x to power r plus 2 plus the rest of the terms. So if I take the first derivative, it becomes the first derivative, it is x to power r. We are taking the derivative, it becomes c sub 0 r x to r minus 1. The first term does not vanish, plus c1 r plus 1 x to r plus the rest of the terms. So y prime becomes the sum Cn n plus r x to n plus r minus 1, and still starting at 0, we still have the first term, which is c0 r x to r minus 1. That's why we start at 0 to infinity. With the same logic, if you take the second derivative becomes c sub 0 r minus 1 x to r minus 2 plus the rest of the terms. So the second derivative is equal to the sum Cn n plus r minus 1 x to n plus r minus 2, and n starts at 0 to infinity. Very good. So we have the first derivative, we have the second derivative, we have the power series that we have, and we need to do the substitution. So I'm going to substitute. Let's see, what do we have? So this differential equation becomes 3x times the second derivative, the sum Cn n plus r n plus r minus 1 x to power n plus r minus 2 plus y prime. Y prime is the sum Cn n plus r x to power n plus r minus 1, and for all n start at 0 to infinity, and minus y, which is the sum Cn x to n plus r equal to 0. Perfect. Now our goal, our job is to try to combine these series, find a recursive relation for our coefficients. Before doing that, let us distribute x here into first series. This guy becomes x to n plus r minus 1. Very well. So as you can see, these two series have the starting index, and the x has the exact same exponent. So you can combine these two series. This guy becomes the sum Cn n plus r n plus r minus 1. And I'm going to distribute these 3 here. It makes it easier for me to do the calculation later. Plus Cn n plus r, and they both have x to power n plus r minus 1. I'm going to copy down this series here. Why is that? Because the exponent for x is different from the exponent for x here and here. Cn x to n plus r equal to 0 and start from 0 to infinity. Now I'm going to combine these two by factoring out Cn n plus r. So if I factor out Cn n plus r, what I get plus 1 here. So this becomes 3n plus 3r minus 2. It's multiplied by x to power n plus r minus 1 and start from 0 to infinity. And this is my second series. We do the subtraction between these two series, but before doing that, first of all, factor out x to power r. Try to make it a little bit simpler. So this becomes x to power r, and this becomes x to power n minus 1. I'm going to just write this here, minus some Cn x to power n and start from 0 to infinity. On the right hand side, I have a 0. Very good. So now what? I have 0, 0, but these two exponents are different from each other. Before making any substitution, making any changes in the variables, in the exponents and n's, let me write down the first term here. I have 0 and I have n to power x to power n minus 1 here. I want them to have the same number, 1 and a negative 1. It makes the shift a little bit easier. So this becomes x to the power r, c sub 0 times r, 3r minus 2, x to power negative 1, and then plus the rest of this series starting at 1 to infinity, Cn n plus r, 3n plus 3r minus 2, x to n minus 1, minus the sum Cn x to the n. On the right hand side, it is 0. Well, if I just make this adjustment, writing, for example, k equals to n, and then k equals to, well, n minus 1, I can find a nice relation between these coefficients. Why is that? Because this adjustment makes this have the same exponent and the starting index. X to the power r, c sub 0 r, 3r minus 2, x to negative 1, plus the sum. This guy becomes k equal to 0 to infinity. Then you have c k plus 1, n is k plus 1 plus r. And here I have 3k plus 1 plus 3r minus 2, x to power k minus the sum ck x to the k start from 0 to infinity equal to 0. Okay, here. Now I can combine these two series. Let's see. I have x to the r, c0r, 3r minus 2, x to negative 1 plus, right? I have the sum. I'm going to factor out x to power k. And then if I distribute 3 into parentheses, I get 3k plus 3, 3k plus 3, 3 minus 2 becomes 1. Okay. And what do we have here? What do we get? We get, well, k plus 1 plus r and times 3k plus 3r plus 1 minus, and let me see, where is my ck? Okay, ck plus 1 minus ck, and this is another parenthesis here, another parenthesis, equal to 0, k starts at 0, goes to infinity. So far, so good. I just combine these two. Very good. Now let's take a look at this term here. On the right hand side, you have 0. It means that these terms are equal to 0. This guy and this guy. So by setting c sub 0 r 3r minus 2 equal to 0, we have the following scenarios. It means that either your c sub 0 is equal to 0, r is equal to 0, or r is equal to 2/3. Am I right? Okay. So far, we have this information. From this, we have ck plus 1 equals to, well, ck divided by this multiplication. K plus 1 plus r, 3k plus 3r plus 1. Very good. So far, we have this information. What are we going to do? We're going to start by plug in 0 for r, and then plug in 2/3 for r in this recursive relation. See what we have. So if r is equal to 0, ck plus 1 becomes ck divided by k plus 1 times 3k plus 1. Okay, this is for this. If r is equal to 2/3, ck plus 1 becomes ck divided by, here you have k plus 2/3 plus 1, 5/3. And we get 3k plus 2r plus 1. There you go. Okay, cool. So far, so good. So let's see what do we have. If I plug in 0 for k, if k is equal to 0, from the first equation, I have c1 equals to c sub 0 divided by 1 times 1, or just 1. If I plug in, well, 0 here, if k is equal to 0, my c1 becomes, well, c sub 0 divided by 5/3, and here I have, there is no 2 on the right. This is 2 plus 1, which is just 3. We got rid of that. 3k, and here we have 3. Am I right? Yes. I forgot to simplify this after plugging 2/3 here. 2 plus 1 becomes 3. So then you can cancel out these. It gets to 3k plus 5. Okay, simplify it all the way. K plus 1. Okay. Do all algebra. Okay, perfect. So if I plug in 0 for k, I get 5 times 1. So what if k is equal to 1? If k is equal to 1 from the first equation, so I'm going to list this here. From the first one, c sub 1 becomes c sub 0 divided by 1, 1, and c sub 1 becomes c sub 0 divided by 5 times 1. And if k is equal to 1, what do we get? If k is equal to 1, well, c2 becomes c1 divided by 2 times 4, but c1 is c0, So we get C0 2 times 4. So this is my C2. C0 2 times 4. Okay, very good. What about this guy? If I plug in 1 here, my C sub 2 becomes C sub 1 divided by, so I get 11 times 3, but C1 is C0 divided by 5, so C2 becomes C sub 0 divided by 11 times 5 times 3. Okay, is that correct? Seems to be correct. Okay. Oh, K is 1, am I right? Yeah, K is 1, it becomes 8. Okay. Plug in 2 here, 8. Okay. Very good. 8 times 9. And this is going to be 2, not 3. Okay, let's fix everything. Cool. So we continue this process. Now, what if K is equal to 2? Very good. We need to find C sub 3. So if K is equal to 2, so C sub 3 becomes C sub 2 divided by K is equal to 2. We get 3 times, and here we have a 7. Okay, so C sub 3 becomes C sub 0, 2 times 3 times 4 times 7. Very good. So this is C sub 3 by the first formula. What about C sub 3 from the second formula? So K is equal to 2. So K is 2. It means that C sub 3 from the second formula becomes C sub 2 divided by, here we have, now we have 11. Am I right? Yes, we have 11 times 3. So my C sub 3 becomes, but C sub 2 is C sub 0 divided by 8 times 5 times 2. So this guy becomes C sub 0 divided by, well, 2 times 3 times 5 times 8 times 11. You can continue this process. If you continue this process, you're going to see this pattern here. So I'm going to erase this part of the board to be able to write down the pattern here and see what's going on. So R equal to 0 gives us CK plus 1, which is CK divided by K plus 1 plus R times 3K plus 3R plus 1. And from this, we got C sub 0, C sub 1 is C sub 0 divided by 1, 1, and C sub 2 becomes C sub 0 divided by 2 times 4. And then let's see, and C sub 3 that we found is C sub 0 divided by 3.
Yeah, Professor, we can't see your screen.
3 C sub 0, 2 times 3 times 4 times 7. I'm just copying down whatever it is on the board so I can move this. So give me a moment. I copy this guy down so you can see this side, and then exactly the same goes up. So R is equal to 2/3, and CK plus 1 is equal to, so here you have 3K plus 1, then make this part, and this guy becomes 3K plus 1. And this guy becomes CK divided by 3K plus 5 times K plus 1. And from our calculation, I'm just copying down our calculation up here. C1 becomes C sub 0 divided by 1 times 5, and C sub 2 becomes C sub 0 divided by 2 times 5 times 8, and C sub 3 becomes C sub 0 divided by 2 times 3 times 5 times 8 times 11. Okay, now let me erase this part of the board. So we move up so you can see everything on top here. By following the patterns, by adding more of these, we have the following case. By continuing, writing more coefficients, we see the following patterns. So it seems that from the first formula, we get CK to be equal to C sub 0 divided by. So what do we have? We have 1 times 1, we have 2 times 4, well, we have 2 times 3 times 4. So it seems like I have 1 factorial, I have 2 factorial, I have 3 factorial. For the next one, I have 4 factorial multiplied by some other numbers. Well, those numbers follow pre-k minus 2, because here, take a look at this, 3k minus 2. If k is equal to 3, what do I get? I get 9 minus 2, which gives me 7. If k is equal to 2, I get, well, I have 6 minus 2, which gives me the 4, and so on. Am I right? Okay, perfect. So it seems like I have the following case. I have C sub 0 divided by n. Let's just write down k factorial, then we can generalize the idea. K factorial times, well, I have 4, I have 7, so I have 4, I have 7 multiplied by 3k minus 2. This is from the first formula. From the second formula, so the first formula come along when r is equal to 0. When r is equal to 2/3, ck becomes, well, let's see what do we have here. We have c sub 0, 1 times 5, c sub 0, 2 times 5 times 8. So I have 1 factorial, I have 2 factorial, I have 3 factorial, and as you can see, 5, then 8, then 11, which are 3k plus 2. Let's double check. So if k is equal to 1, I get 5 back. If k is equal to 2, I get 6 plus 2, 8 back. If k is equal to 3, I get 11 back. So I have the following case. I have c sub 0 divided by, well, k factorial multiplied by 5 times 8 times 11 times 3k plus 2. So far, I found these relations for my C case. So y1 is equal to, remember that we had the general solution written as y equals to sum cn x to power n plus r, and n start from 0 goes to infinity. X to power r is equal to 0. So y, the very first one, related to r equal to 0 is equal to the sum. You can just convert this back into n, c sub 0, divided by n factorial times 4 times 7, 3n minus 2, n start from 0 to infinity, and we have x to power n, and r is equal to 0, so you get x to power 0 for r, which is 1. And the second solution can be written as the sum c sub 0 x to n x to 2/3 divided by, here you have n factorial, 5 times 8 times 11 times 3n plus 2. and start from 0 to infinity. So we found two linearly independent solutions for this differential equations using power series method.